simplest safe integers. That's the topic of today. I'm Peter Sommerlad. The talk slides are online. You'll see the QR code and the URL. I put everything on my GitHub, and as this is CppNow, the slides are just recently uploaded a couple, maybe 2 hours ago. So there we are. So what is the issue with integers? One thing is we have signed integer arithmetic with undefined behavior. Many programmers aren't aware of that because they just assume they will wrap around, or maybe they have other properties, and most of the time they are not aware of that undefined behaviors until recently, when compilers started to be able to prove that there's undefined behavior and just remove the corresponding code, because undefined behavior means anything can happen, and especially nothing. If nothing happens, that's very nice. So if you look at this example, if you multiply 65,000 something by 32,000 something, that gives us a very large integer. And if you're on a 32-bit machine, that prints nicely the number I'm giving here. But what if we actually go to 65K times 32K, and what will that print? So with 32-bit integers, that will give us an overflow. And because it's a constant, actually compilers will warn about that constant arithmetic, but consider if that's not a constant, you will end up with a silent integer overflow, and that means undefined behavior. So your hard drive can be formatted, or your computer explode, or whatever. And one assumption many people have but never check is actually employing standard numeric limits. There's a flag called isModulo that tells you if the integer type that you're using does actually wrap around or not. And for regular int, it will actually return false. And if anybody knows what's printed here in seriously, can put that answer in the chat if you like to. And I'm still trying to get rid of my echo, and I might just turn off my iPad. Okay, what else with the sound? Without the sound, and it's still the sound, and I have no idea where it comes from. So when we want no undefined behavior, we can actually use unsigned arithmetic. That is guaranteed to wrap around, to have modulo semantics, and even that can be critical if you want accurate results. Unsigned arithmetic will never be able to tell you that you actually are having the overflow happening. So that's also a pity, and I will show you in the very end library where you can actually detect unsigned overflow as well, at least in a configurable way. So why is undefined behavior problematic? There are domains where safety critical systems, or even security critical systems, where undefined behaviors really occurs, and you will get into problems of that physical harm, or maybe data loss, or security incidents will happen. And for the safety critical part, especially for vehicles, there's the MISRA-C++ guidelines that will are talking about how to use a subset of C++ to, let's say, reduce the risk of getting into undefined behavior, or getting into writing code that might confuse the programmer. And I'm currently working with that group on getting a new release out, because the current MISRA-C++ guidelines from 2008 are quite dated and are not accommodating what modern C++ should look like. And for example, one recommendation MISRA-C++ provides is giving you the telling you not to use the standard integer types, especially because their sizes are implementation defined. And we have the C standard int header, or in C it's a standard int.h that predefines exact with integer types on most platforms. And so many of the guidelines actually are trying to prevent undefined behavior and to guard against developer confusion. Now, what do I want to achieve with a special integer library that doesn't use ints? So I want to mimic MISRA-C++ built-in types restrictions. For example, the MISRA guidelines tell you that you should only use unsigned types for bit operations, or should never use character types for any kind of arithmetic. So while the MISRA guidelines are typically supported by static analysis tools, where there are plenty of vendors who provide at least the 2008 guideline set, it's even better when you don't have to have an extra tool, but the compiler just won't compile the code that does it like that. And that's limiting the available operations. That was also the topic of my strong types talk yesterday, or many of the strong type talks we had this week. So even though you are obliged to use a static analyzer, it's better to be able to write code, get the immediate feedback, so you never get into the situation that you get some positives from the static analyzer, at least with that respect of that domain. So one thing that's also banned, I already said so, you shouldn't mix character types with integers in arithmetic. And if you do it without any special preventive measures or a static analyzer, you will actually easily to be able to do arithmetic on character types, especially the smaller ones will happily promote to int and then continue to work in arithmetic, which can give interesting results when it was unintentional. A big curse of our current built-in type model is integral promotion, especially since smaller unsigned integer types actually promote to signed integer. So even if you specify your variables with an unsigned integer type, you might end up doing arithmetic in a way that causes undefined behavior, because before the actual arithmetic happens, they are promoted to a signed integer. So my goal is actually prevent signed integer undefined behavior, but implement wrapping so that you at least get some results, even if the numerical results are wrong. At least the compiler will not optimize away your code by saying, no, it's undefined behavior. And another thing are the many silent conversions we get with our built-in types. We happily convert from bool to numeric types and back. We happily convert between or silently convert between floating point and integers and forwards and backwards, depending on the context where something is used, and in combination with overload resolution and implicit conversions can really be a nightmare to figure out when things go wrong, why they went wrong, or giving you developer surprises where then a specific function overload or operator overload is selected that you weren't aware of even existed. And what I still allow is widening of the same signedness. So if you combine the U in 16T with the U in 32T, the operation is valid and the widening happens automatically, because that is a safe way to actually do arithmetic, and the result will be of the wider type. And the goal is also, that's why I built that, because the strong type library uses structs, even if they are trivial aggregate types. You might end up in compilers getting worse code generation than with the built-in type. With the integers and or using enums, but that's my approach as integers, the generated code, as far as I could observe it so far, is absolutely identical if you would have used the built-in plain integer type. Now, my goal is actually to have enums as integer replacement, and there are some limitations on that approach. We cannot have implicit conversion, at least when we use enum class types. You shouldn't use, let's say, regular plain old C enums anymore, because those will happily convert to int or other integer types, so you don't get the protection against silent conversions that I actually wanted to prevent. We need the disadvantage because we don't have constructors for enums. We need our conversion operators. We need explicit named conversion functions that might need to check if the conversion is actually valid and desired and wouldn't lose any information, so it's not narrowing. There are some operations where we cannot easily define the full range of input. For example, we cannot divide by 0. Even if we do that in an for an unsigned operands, we will still get undefined behavior. The same situation happens with left or right shifts. If you try to shift more than the actual number of bits, there is at least implementation defined behavior. What will happen then? And the thing is, those things are detectable only, or are detectable at runtime, but what to do about that? The detection costs overhead, and that's deliberately, I put that in, so you cannot divide by 0 with silently, but and trace fall into a trap. But there are different options how to actually denote the error, and I have chosen here to provide 3 different ways: throwing exception, having the good old plain asserts, or return 0 if you're in production mode. That is a safe return result, even though it's wrong. It's better than having undefined behavior or trap the system then. So the actual implementation uses the enum class, which prevents implicit conversions. That's the same approach the standard uses with the standard byte, which is an enum class of the size of an unsigned character, and it wouldn't silently convert to anything else. And that's the idea behind my approach as well. With enum class types, you can have operator overloading, and concepts help you to constrain the overloaded operators, so you don't have to spell them out for each individual type. Plus, they won't be considered for any other enumerations and so on. And since we are now in C++20 and compiler supported now, the user-defined literal operators, that makes it easy to generate constants of these types, so you wouldn't have to spell out them as names. Const eval guarantees that these UDL operators are computed at compile time, and that way we can ensure that any too big numbers that you want to convert to too small integer type will be actually detected. And if you have I hope the PDF will end up being able to have the links here, but I will provide you later on with the corresponding paths where to get the library to look at. It's a single header only library, so that should work nicely, and you can even try it on Godbold. The README provides a link for it to play around with it. Now, what's the actual 8 types that I define? It's for all the standard unsigned integer types that have a fixed width. I define a corresponding enum class type, and we will see why there is a single enumerator that is given here later when we see how it's used to distinguish this enum class UI8, for example, from standard byte, who has also unsigned char as its base time, which is corresponds to U&AT. Now, how would the user-defined literals be implemented? We put them in a separate namespace, so you can actually avoid polluting your namespace when you use them, or directly use the namespace of the safe integer library. And we have const eval, so it's guaranteed to be computed at compile time. We have the desired return value and the suffix with an underscore. We have to have the leading underscore because it's a non-standard user-defined literal. And the only reasonable thing that I could come up with having an unsigned long, well, user-defined literals, because we that provides us with the built-in hex or binary encodings or octal and decimal without going any hassle of self-interpretation. There have been talks by me in the past where I showed how to do DIY numeric parsing with UDLs with have the arithmetic template parameter of character type, but that's not where you want to go. It should be simple, not show off code. And to make sure that it's actually a valid version, we compared with the numeric limits of the underlying type and see if that matches the maximum. And so it's a valid version of that, and return the corresponding casted value. So we use a cast expression here. We cannot use curly braces here because we have a narrowing conversion from unsigned long to whatever we get here. So it's UN16T wrapped in an enum class type, and we want to make sure that this cast happens. And because we have the check in front, it's safe because we know the value will always fit that type. Otherwise, we perform a trick that will trigger a compile error whenever you, in a context-to context, try to throw an expression. At least until now, until we get, let's say, compile time exceptions, which hopefully we don't have yet. This will trigger a compile time error. There are different approaches how to get there with the compile time error, like accessing undefined, calling an undefined function, but that will then come later at link time, for example, when this function is never defined. How can we use that? Okay, we use our literals namespace, and then we can actually use our UDL suffix and be able to create a corresponding variable. And we can even use here the direct cast, and this is not a narrowing conversion because we have a literal, and then the compiler can check if the literal fits the corresponding type, and it will actually compare equal. And here are two cases where the actual compile error is happening. This is would be a literal that is too big to fit in a 16-bit integer, and that will give you the corresponding compile error that we just have seen with the throw expression there. And we can even try to have a narrowing detection, and if it's too big, again, the compiler will complain without any special means that it wouldn't fit there. Now, some traits to be able to actually have good conversion functions. And one is I just defined a shorthand for remove CVREFT because that's quite a long trait. And if you use it several times in a single statement or expression, or declaration, it's really annoying to have it there. And the code would no longer fit on the slides, even on widescreen. So I create my own trait that gives me the is-enum v, and I'm using that plane to actually make sure if it's used somewhere where something is const qualified or even volatile qualified, it wouldn't get there a reference. It would still get the plain underlying type that I'm looking forward to. And with that concept that I just defined, an enum, I can actually constrain now my other traits that I'm about to define. So the next concept, the next trait actually except is only applicable to enum types, and then we define a context variable to see if it's a scoped enum, and that's a trick that's actually proposed and accepted for C++23, where you check if the actual enum type is implicitly convertible to its underlying type. Sorry, and that is what the enumerations unscoped enums are allowed, and the not here, the little exclamation marks, will negate that. So whenever you're not when it's an enum and it's not convertible to its underlying type, then it's definitely a scoped enum. And together with the is scoped enum, I usually use is underscore for traits, let's say consecutive bool variable, so traits, and I have started to use the prefix a underscore or n underscore to name the corresponding concept. This makes it easier for me to distinguish what is a concept and what is a trait, because they more or less very often come together. And why did I use a trait anyway at all here to define the concept? It's mainly because I also want to provide a C++17 solution where you don't have concepts, and having the trait already defined helps a little bit in that porting. Now, with if you're familiar with the detection idiom in C++17 and earlier, then you might already have, and not yet with concepts. This is how you would actually implement what is called the detection idiom by just defining corresponding concept, which makes it easier. So we are having, again, a trait that we define is a safe int. And in general, nothing is a safe int except for the 8 different types that we implemented. One approach would have been to actually specialize is a safe int for these 8 different types, but I wanted to show off and show you how to use concepts. So whenever we have a scoped enum, then maybe a safe int is true. And to actually compute true, we have a requires clause that gives a requires expression that will check at compile time if a given syntactical element is actually valid. And that's the E is the dependent type. And we actually check if a default generated E, that's our enumeration type, actually is equal to this strange enumeration value that we actually defined for our 8 different enum types. The hope is that no other enumeration class type will actually have this member or this enumerator, and I deliberately have chosen the very long name to make sure that it's not accidentally chosen by anyone. And again, we could have made that directly a concept, but I wanted to have the trait and the concept together to be able to use both in later on. Now, whenever we write code like that, we should actually check that, and checking is easy with static assert. So I put those usually in a separate namespace, or because I want to not have to write the namespace that I'm using everywhere in front of it, but it's that those things are easily refactorable with my preferred IDEs develop. So I check all the traits here if all my 8 different types that I defined are safe ints, and then I have a few other test cases for the negative part. I check that int is not a safe int, and that standard byte is not a safe int, and even that specific enum class is also not a safe int. Now that's the basics. Now, one thing that I wanted to actually address was the promotion with the same sign. So I allow integral promotion because we actually have to make the arithmetic somehow map to the built-in types, because that's where the arithmetic operators are actually defined. And but we don't want to promote an unsigned character or uint8t or ui8 to a signed integer. And how to get there requires some metaprogramming. So we actually compute at compile time the to be promoted type. Promoted type actually checks if the promotion is required. So if the size of the underlying type of our enum class type is smaller than an int, that is when actual promotion, integral promotion happens. And then we check again if it's an unsigned type, and if it's unsigned type, we promote to unsigned. If it's a signed type, we promote to int. And that's where we actually changed the built-in rules of integral promotions for smaller integer types. Now, to make use of that, I again have a shorthand for the underlying type. So if it's an enumeration type, I used it. If it's not an enumeration type, I use a plain type, and that's mainly there to prevent the code from giving you compile errors when it's when you more or less try to promote an underlying type that's not an enum type already. Now, the explicit conversion to an integer will use that integral promotion, and that is done by just static casting our enumeration value to the corresponding integer type that we computed with the promoted meta function. Now we should test that as well, so we can actually check if they the toInt of one UI8 is actually promoted to an unsigned, because to check that we actually add the 1, and this expression will be computed as an unsigned expression. If the left-hand side is actually an unsigned, it will be computed as an assigned integer expression if the left side of the plus operator is promoted with the built-in type rules. And this is how we actually check that the unsigned promotion actually delivers unsigned. And for the signed integers, we just assume that the promoted type is the assigned integer, and that's also working well. Now, to be able to convert the other way from integers, regular integers, to our special enum safe integers, we need to check if the integer type actually matches one of the underlying types. And this box is pinkish to show you, okay, this might not have been the best idea, but this is the code I started out with. So we have our 8 different standard integer types that we are using. And this code checks if the type that you want to convert from is either one of these 8 different integer types. And if this would have been an interactive session, I would have asked, what is bad? And expected an answer from the audience, which we won't get here. So I have prepared some slides to show you what is actually bad here. If we look at the definition of these 8 fixed size integer types, we actually get this, and I copied this together from C standard int of one of the implementations, and we see that the assigned character is actually the int 8t, short is int 16t, and int 32t is int on my machine, and int 64t is long on my machine. And now, if you really know the promotion rules very well, you might already guess what's the problem. And the problem is, if you look at integral promotion rules and implicit conversions from our types, we know that we have the conversion rank from character, or promotion rank from character to short to int to long to long. And if you look at the left-hand side of the types F, or if it would have been written as using declaration on the right-hand side, we see that long is missing. But long is distinct type from int and long. So it has a different conversion rank. And if we have a constant or variable of type long, it would not fit what we would have on our is same. It would never be true, be matched here. So is integer v would actually be false for long. And that's not very nice. So long is missing. What can we do about that? Well, is same might be too restrictive, so we would actually need to check if it's the same range of values that is representable. And how we do that? Okay, we define another trait to go there, and I named it is compatible integer. So it's either is same, then we are done, or it's an integral type, which is a standard integral, and it has it's not bool, because bool should not be an integer, at least not not in my book, but we have that and we cannot get rid of that. So I prevent of a bool being converted to one of these special safe integers. And also we check if it's a character type, because we want to prevent mixing character types with arithmetic. And even though if they might have the same values, so they are distinguished. That's there because the MISRA guidelines are separating the character types. And some people might argue, oh, I cannot then write my, let's say, Unicode library that does all the interpretation of these character types. You cannot do that by following that specific MISRA rule or using my safe integer library. But that's okay. If you've wrapped it in a library, you can get an exemption for that library only and make sure that the users of the library just use the library for doing the correct way of dealing with Unicode or whatever character encoding you're using. We check for the same signedness, so that's the equal sign here. So either both are unsigned or both are signed, so we don't get the signedness change when we want to convert the integer values. And then we check if the numeric limit max is the same, and that gives us, okay, both types have the same range. Either they have both signed and have the same maximum, or both unsigned and have the same maximum. And that is where we actually want to go for. Now, to get to the similar thing, we look for, we define it as a shorthand for is compatible integer. Why? Because it started out with is same, and I just wanted to make the minimum change to the code that we have seen before, and to make it fit on a slide as well. So, but before we can do so, we have to show what is actually the character type. I already taught you the rationale why we want to make that special. So I check again now with identity type identity again if the type is equal to character and not signed or unsigned character, to either that abomination of white character T, or for C++20 and onwards we have char AT, and this also shows how to go around with the macros that give you the feature test macro. So if that macro is actually defined, then your compiler provides char AT, and in C++17 mode, for example, it might not have defined that type, and then this line will not be included in the compile. And the same for the Unicode types char 16T and char 32T. Now, we changed our is known integer from is same to is similar, and we actually check the range of these tests of the types, so that long will actually fit on my machine. It will fit the int 32T because it has the same range of values than int, at least in the mode I'm compiling with. And we define the concept again by saying, okay, an integer, which maybe should have a better name as the safe integer of the safe integers that we are talking about in my library, it's the same as is known integer. And now we can re-implement our meta program or adapt it to use is similarly to our that failed attempt with the is same v, where long wouldn't match. And we have that long to convert from an integer where the type is deduced here, and we make sure that it's actually an integer, not something, not a character or what else. And we check if it's similar to any of these built-in or the compiler provided fixed with integer types. And because the syntax of, let's say, we cannot have conditional T without a final else, we have to provide a type here. We could have used void, but I have chosen to use a specific type that is just defined locally, and I'm using that to get a better error messages instead of a strange one. And in the again, from our computed result T, which is one of our 8 integer safe integer types, we will actually cast to that type and get the corresponding enum value from the original value. Okay. I also provided directed conversion with this kind of a static cast. So I convert from a given integer to maybe not the matching safe integer, but from a different one, which can be helpful if you want to convert, let's say, literals, or let's say integers that you get from an API or some other functions where you know, okay, it's definitely in the range that will fit, and but I want to make it an let's say a shorter integer on my system where it wouldn't fit, or maybe even a longer integer, because I know that I will use it later in an expression with the longer type. So what we do, we're taking the result type and look what is the underlying type of the attempted result type that we want to convert to, which is given as a template argument to our from int2. And if that's an unsigned type, we check if it's greater than 0, because the from type could actually be a signed integer, so it should be greater than or equal 0. And if it's below the numeric limits of the maximum type, and if that actually is true, we return the corresponding cast, and otherwise we have a throw expression to throw an exception. And you might have seen, I already have told you, okay, I have 3 different means of having operations that might fail. And we will see this might be over-engineered, how to actually make it the code a little bit simpler later on. And for signed types, we have to check if the value is between max and min. And if that's happening, we happily return the corresponding casted value. Now we should actually test those conversions. And we can check if a uint8t value actually converts implicitly to the corresponding UI8 type, and that's what's checked here at compile time. And with a signed integer, we can actually check it to convert to tell it to convert to a signed integer of 8 bits, and because 42 is smaller than the corresponding numeric limit max, it works and fits there. And if we attempt to do that with the character type, like the space character, we will get a compile error because the corresponding logic will not allow us to use a character type here. And the same is there for bool. We cannot convert bool accidentally to one of our special enum types. And we can even check the throwing if we want to convert a too big value to a too small integer type with the from int2 that actually throws an exception, or not an exception, a character pointer, because that's the argument to the throw expression. I didn't want to throw a standard exception because I didn't want to have the dependency to the standard except header, because this code might actually, people might want to use this code on systems where exceptions are deliberately disabled. Now we have some checks where we actually want to check at that the thing doesn't work at compile time. So how can we actually make the checks for what's given here that shouldn't compile? And not being able to compile something is again possible with the detection idiom. We define a corresponding trait from int compiles, which is in general false. And we have that extra template parameter that we then use for the specialization, where you use the standard void t, which is available in C++17 for implementing the detection idiom. And look if this expression is actually a valid expression, can be syntactically formed, and it will not be evaluated, but we check it. And if that actually is a valid expression, decal type will be happily return its result, which is then ignored by void t. But then this specialization is a better match than the more general specialization, and the corresponding value of the from int compiles is true. Just a little gotcha. If you forget the blank here, you get very interesting parser results because of the max munch parse of C++. So even though we can now place two angle brackets next to each other, you will not be able to place the equal sign for a trait that you define next to the angle brackets, because that will actually be parsed as either greater or equals or as a right shift here. Interesting compiler error messages if you forget that. And with that trait, we can actually check if that from int compiles with long. And I more or less implemented that because I figured, oh my God, long is not working. What have I done when I showed you the red code? And we can see that bool and char cannot be converted with from int. Now, when you write test cases for your framework, you get the equality and relational operators for enumeration types by the compiler, but what you don't get is the output operator. And so we have to provide an overload, and we use the concept here to limit the overload to just our safe enum types, our 8 different types. So we only have to spell it out once. And we convert it to an integer as a value, and this ensures that actually integral promotion happens. So we don't print out a unsigned character or a signed character as the ASCII code that the regular shift operator might do for you. Now, this is how I prefer to spell concepts today, constraint functions, to show, okay, it's a template function, and you can do that in a shorthand notation by using the concept name and auto as the parameter type, which is kind of convenient and shorthand and might be able to not shy away new programmers who are afraid of templates. But again, it's kind of easily to miss that you actually define the template function here that adds to the corresponding overload set. So I'm a little bit torn. The shorthand is convenient, but it's also hiding the fact that this function or this operator function here is actually a function template. But your mileage may vary, and maybe in the future my opinion will also change, and I'm doing auto everywhere. Now, as an example of arithmetic operators, if you consider, okay, we use two safe ints, they might not need to be the same, but we also want to make sure that they have the same signedness, so we don't mix signed and unsigned versions of our safe integer types together. So we have a requires clause here that checks for the same signedness of our safe int types. And that way we get the promotion. So we actually look if which type actually is a wider type. If they are one is wider, we select the wider type. Otherwise, we select either one for the result. And to actually ensure that the operation is done as unsigned, I have a conversion function toIn that works to uIn that works like toIn, but unconditionally always promotes to an unsigned type, and that ensures that the plus operation is actually the built-in plus operation for unsigned, which will have the modulo semantics and will wrap. So you might get the wrong results on overflow, but you will never get undefined behavior here. And in the end, we cast back to our result type in the end. And this intermediate cast is actually there to guarantee that we get the not get a warning and not get and have the actual result type that's expected here for the corresponding result type is the safe integer enum class type, and we will get there from the corresponding underlying type. Now, to make sure that my code generation is actually optimal with so much scaffolding around that it's actually just compile time stuff that's happening, and that the plus and the other arithmetic operations are working, I wrote a very small test program that allows you to have different operations, and to make sure that they are not optimized away by the compiler. I don't make them const expert and use a standard algorithm, just taking an initializer list of values, and these are some Fibonacci numbers, and use accumulate, so that will apply the corresponding operator over and over again, and we will see if that's the same code. And I implement that as a function that takes the regular int 8t and one of our special integer types, and you can play around with that on Godbold, and this is the Godbold, the corresponding Godbold link. And the code generated is absolutely identical, except for the label names, because it's in the same file. They will have different label names because of the different functions. And I checked that with the diff tool. And on most operators, in most arithmetic operations, it was actually identical code, except where the processor has different assembly instruction for, let's say, integer division that is signed or unsigned, for example, or integer multiplication between signed and unsigned. There are some smaller differences, but not in difference in let's say, parameter passing or whatever when you do that. But you can figure out yourself. Now, we have, like with the plus operator, we have all the arithmetic operators provided. We get the comparison operators that are bound to the individual types for free, and we don't get comparison operators with the other integers, and that's good. So, as I told yesterday in my in my strong typing talk, that comparison between distinct types is usually not a very good idea, and that there are only very, very few exceptions where it might be convenient, and even then it might not actually be the best way to go forward. Unfortunately, the standard allows too many cross-type comparisons already. Now, how get we rid of all the undefined behavior? What can we do with operators that might fail, like the division modulo by 0, or might have implementation defined behavior, like the left-right shift with too many bits? And there are three fundamental options in, let's say, in normal C++ code that might not be embedded, or not where exceptions are enabled. We might actually throw an exception on some platforms that I'm trying to target, especially those where the overhead of having the exception facility and the corresponding runtime type information is too much. This might not be a viable solution. On the other hand, we definitely want to, even on those platforms, while testing, we want to make sure that we detect any of those errors, because they actually are programmer errors. So we want to have asserts, the regular assert that will cause an abort of the program, and that might be okay for those platforms. And the last option, if you really want to run in not in debug mode, but in release mode, and where assert would just go away, you still want to have a reasonable behavior that's not undefined. And that is where we provide the means to return a wrong result that is better than just undefined behavior. And we will see what that wrong result should be. And to get there, we have to rely on macros. So first, let's get to the case that's interesting with the returning a wrong result. So we have a macro with not just the condition like assert, but with the default value that we will return in case the assertion fails. And the caller of the macro is responsible that this matches actually the function return type. So and then we use a trick of C++20. If it's actually constant evaluated, we can make the code fail to compile. So if the compiler can detect that you're trying to divide by 0 because you provide the literal 0, then we will recognize the error. So it will even trigger if you compile for release mode at compile time, if the compiler can detect it. And if the condition is violated, we actually use the throw statement, and this will definitely be a compile error, because if it's constant evaluated, you're in a context, and there you cannot throw exceptions. Otherwise, you're actually at runtime, and then the only thing that we can do is because assuming we are not throwing exceptions, we just return the default value to avoid the undefined behavior. If you're not in debug mode, we have two options. One is, okay, we compile with the throwings asserts, and then if the condition is wrong, we throw the condition. And if it's because we want to make happen to make the function that have these asserts in not actually terminate, but actually throw the exception, we then have a special macro that marks them as no except files, which in other cases will just mark no except, so because there won't be a throw. And if we have assert available, we just use the assert macro that we are happily using here. Now, how can that be used? Okay, for the division operator, we assert that the divisor is not the default value, which is 0 for an enumeration type. And in that case, we might return result t. And to get a little bit nicer error message, we extend the condition by a logical ampersand, giving that string. That's a trick to be used. And we have to use that because we don't have the any other means to get additional text right now into the assert case. And this will actually fail to compile if the context function is executed at compile time. Otherwise, we will have a runtime problem that we just discussed here. And in the end, we use the same trick as for the previous for plus by casting everything to unsigned before we actually use the operator. We prevent the potential. Well, there's no potential overflow, I guess, in division operator, but just for symmetry. Now, how can we test these things? We have 3 different compile paths to our code, and we want to test those. And the end debug case, actually, okay, we want to make sure that we actually get a 0 result from a division by 0. And in the case of the assert throws, of the throwing part, where we have another macro specific to the framework to make sure that it actually is throwing. And in the assert case, we actually cannot test the program abortion that happens from the failed assert, but we can cheat and make it just test when a test case fail when it's there. And there are some things to prevent the compiler warnings. But how can we actually test that this doesn't even compile if it's executed at compile time? So we want to make sure that if we have a constant expression where we divide by 0, that this doesn't compile. That would be cool. Now, everything that would be cool usually requires macros, and these are the macros that check does not compile, and we check does not compile actually checks that division by 0 for assigned integers does not compile, or checks that left shifting assigned integer does not compile, but left shifting an unsigned integer does compile. Now, how can we get there? We even want to make sure that when we have a shift by too many bits, like 8 bits for a U8T, that this will actually fail to compile. One trick I'm using, it's just here on this slide, I should have put it on the next one, is I define a similar thing to void t. Void t consumes all types and just delivers void. We have a similar thing that consumes values and delivers void. So this is consume value. So that's the void t for template, the non-type template parameters. And this allows us actually to use compile time expressions and check if they actually compile. That's the underlying trick. To get there, we put traits, expression compiles, each in a different namespace, so we don't have to have too many different names. And we create that namespace from some name plus the corresponding not or not, and the line where it's actually called. And to get that concatenation, we have to do the usual preprocessor, the trampoline trick to get the token concatenation operator work with macros, and that's how it's done. And you might have seen code like that throughout. I just implemented my own, not to depend on any existing other headers. So our expression compiles usually is false. And how do we check if the expression actually compiles? So the most common thing is I want to actually check if an operator is available. So I use my consume value as the second template argument for specialization and put in a default constructed value of the template parameter, the macro parameter operator, which might be the shift operator, but also a more complex expression. It just must fit between two default constructed values of that specific type. And if that actually compiles or is expressible and is evaluatable and can be evaluated, this expression compiles will happily evaluate to true. And again, remember to put the blank here. Just don't make that silly error that happens to me all the time. And this is just a trait. Now we actually have to check at compile time that this trait is true or false, depending on the macro argument not. So we check for not, which is either empty or not. Expression compiles for a given type and then generate a nice error message that will generate what we actually provided here and gives us the expression that either compiled or didn't compile if it's wrong. And that's a trick I personally haven't seen yet somewhere else, but I'm sure others have invented that as well. Just having the ability to consume values and having, let's say, more flexible template, non-tab template arguments in C++20 makes it a little bit simpler and easier. Now, what is actually checked? So when we actually check does not compile the shift, we actually check if a default constructed assigned integer 8 and can be shifted by assigned integer 8, and that just doesn't compile. Again, for unsigned UI8, it should compile and so on. And we see that the modulo for signed is not defined because I wanted to prevent that people scratch their head and try to remember which direction the modulo actually computes the remainder. It's always something where I never know what the output is, and MISRA-C++ forbids the use of the modulus operator for signed integers for exactly that reason, because programmers might just guess wrong. Now, if we checking that the divide by 0 actually works, we can actually check the default variation by putting just a slash here, because our default created value is 0. So we divide 0 by 0, and that is actually checked at compile time, evaluated at compile time, and it will not compile at compile time. So the assert here actually will guarantee that it's not happening at compile time, which is kind of cool thing. So we can check with other values if they are invalid and not happen at compile time. If we want to check, let's say, concrete expressions between our interesting parts, we can actually use the parentheses and the plus operator, because adding 0 isn't adding to the value, and we can actually check if these operations actually work. And If you want to mix the signedness, we can actually check if the 0 of type UI8 can be added with the 1 of SI8, and that shouldn't compile, and actually that checks quite well. Now, what else? With that PS assert, we can actually improve our from into by, instead of having that if statement, having an assert there with the corresponding condition and return the default value, and returning 0 in the case you're out of bounds is the safe way to do in production mode, because that's always a valid value, even if the conversion doesn't work well. But there's one problem. If we compile with -n debug, we have that throw here in a path, in a code path that is if constant evaluated. And GCC happily tries to check if you have a throw expression in the non-expr const-expr function, and because if you have a throw expression in a no except function, it will tell you, okay, this give you a warning, this throw expression will always call terminate, which is a nice warning to have. But because this throw expression will never happen at compile time, it will actually never call terminate. And that's a kind of a bug in the checker of the W terminate handling. And that gives us, let's say, working around compiler, I wouldn't say bugs, but let's say too gracious warnings always requires a kind of a little bit of work. And so you get have to uglify our code with pragmas. And so the corresponding thing to disable a warning for a small piece of code. In specific cases, you have the pragma GCC diagnostic push and the pragma GCC diagnostic pop. So you get in the same warning state afterwards. And then you would say something like pragma GCC diagnostic ignored, and that warning that we just had, W terminate. The problem is Clang doesn't have that warning flag, so it warns on that pragma line. And if you have W error as your compiler option, you just try to fix one compile error and get another one on Clang. And so I have to check if it's not compiled with Clang, and then we actually do that pragma with the diagnostic. And there might, whenever I be able to get it compiled with MSVC, there might be more ugliness here, or maybe then the corresponding GCC warning has been fixed by that. So that's the woes that you get when you first attempt to port your code to a different compiler. So it's worthwhile doing so. Now, what's missing still is to get it work like the interesting stuff is that we also would like to provide standard numeric limits specializations for our types. And because we cannot specialize, let's say we cannot partially specialize numeric limits, but we can use a concept here to actually partially specialize. That's interesting. I figured that when I backported it to C++17. So for all of our safe int types, we provide a specialization of standard numeric limits. So this is actually namespace std. And to be able to defer to the underlying type, we actually have a shorthand for the underlying type and delegate almost all of the numeric limits to the corresponding numeric limits, either member function or member variable of the underlying types. Like here, digits and digits, except for is modulo, where we unconditionally say, okay, that is true because we have modulo arithmetic, we always wrap around. And also, we never want to run into undefined behavior, so we turn off traps and say it never signals, so it's never traps. You always get a good result. I'm not sure if any code out in the world actually makes use of that traps rule, but it's there for your convenience, so you can check that. That are all the tricks there. You can look at the source code for more stuff. And a little bit, I backported all that with a lot of concept stuff to C++17. And there's a C++17 branch where you can actually, that you check out and work with C++17 if you have to. And the backporting is interesting. You have to, I didn't do too fancy constraints. That's also one reason why I used the template syntax for constraint functions instead of the constraint function syntax with the concept auto. And this allowed me to actually translate all constraints to enable if other CNI techniques. And it just makes the code much uglier than it used to be. I also made the C++17 branch still compile with C++20 and use the concepts. So there are a lot of if-defs to show that still include the C++20 code in parallel with the C++17 code. The one thing that cannot happen, you cannot actually partially specialize numeric limits. So we have to specialize numeric limits for each individual type that we get. But that's possible by having inheriting from a trampoline where we actually define our numeric limits like we used to specialize it in general. So we only have the single constraint partial specialization of numeric limits and delegate the 8 different specializations for our 8 different special integer types to that partial specialization of the non-related numeric limits type. Just to show you the ugliness, what's happening if you have, let's say, a constraint template with the safe int trait, you will get the we'll have to mimic that with enable if t and the constraint that we had with the trait plus some other saying, okay, is it signed? And then we do the operator minus, and the signed was actually constrained with the requires clause here, and that translates to the enable if up there in the template parameter. The rest, the actual implementation remains the same, but it's really, really ugly. For those who want to know what this means, actually, that's how two's complement is defined. You take the one's complement and then add 1, and that's how two's complement is defined. That is all I wanted to show you on the technique, but if you really want to do safe numerics with integers, my library might not be the best choice. There are other libraries that take a different approach. They use structs as wrapper types around integer types and provide much more versatility with the corresponding types, for especially with error handling that you usually can plug in with the template arguments. There's Boost Safe Numerics by Robert Remney. And there's also a library that does more than just safe integers. It does provide fixed point arithmetic by John McFarlane, compositional numeric library. If you really want to make sure that your integer or fixed point arithmetic is going well and not having bugs, then that might be a library to employ. I know John is using it in safety critical systems, so it's really can be useful. So before you consider my, take a look at them and compare them. I didn't want to compare them. The PS Safe int is the focuses on simplicity, on implementation and usage. I hope it's simple enough to be used. At least it doesn't come with angle brackets for its users, except for the explicit casts. There might be more libraries, but I only took a cursory look, and those are the ones I'm aware of and that I have played with so far. Now, wrapping up, the library PS Simple Safe Integers is free to use and download. It requires C++20 unless you check out the C++17 branch. My target audience are embedded developers or safety critical system developers where, let's say, integer over undefined behavior on integers is a curse. And it's best if you have additional static analysis or checkers that actually prevents you from accidentally using the regular integers. But that's more. And now let's go to questions. And there are some on the chat. I have to lean forward because it's I couldn't enlarge the font on Zoom chat. So the first question is actually the output of my question and give the correct answer, and that is something I to figure out. So everybody has hopefully seen that. Now, there's another question that just became the top one. Have you benchmarked compile times in C+ or 17 branch with this CNI compared to the C++ 20 concept? Is it even noticeable? I would say my test cases aren't big enough to make a difference. If you're really interested in, you can look yourself in the GitHub actions. If you can see a difference in the runtimes of the GitHub actions, which are dominated by the rest of the GitHub and not the actual compile times. So I'm not sure if it's noticeable or not. And I don't have a big enough benchmark that would use enough code to actually where you would be able to detect the difference. So if you would happy to help me with that, I'm happy to put that in the repository and provide that information. Thank you for the question. Now, in numeric limits, why didn't you forward modulo to modulo of the underlying type? I'm answering that as well. I tried to say that already, but modulo is usually false for signed integer types because they have undefined behavior. And I wanted to deliberately get rid of that undefined behavior by making the signed integer types that are defined actually wrap around. That's why I put is modulo true for all of them. There were is modulo true for the unsigned types. That's how unsigned types, integer types are defined in C++ and C. But my assigned integer types are modulo as well. That is why I actually deliberately set that to true. And I hope that answers the question. Now, the last question, specifications states that numeric limits is specialized for the arithmetic types. Your types are not arithmetics. They will not return true for its arithmetic trait, nor do they fit the definition of arithmetic in the standard. So why is specializing it an okay thing to do? I've looked at other safe integer libraries and they provide specializations for numeric limits. And I'm not sure if arithmetic is actually a trait that has to be true for all numeric limits specialization, because arithmetic is defined only for the built-in types. And the standard provides numeric limits for all the built-in types. But I believe it's viable to provide you specializations for numeric limits for your own types, even if they don't match the built-in types, or especially that they don't match the built-in types. I would need to check the standard text if it's allowed, but I would like you to do as well and tell me if you figure out it's really forbidden to do so. So the last question is, that's currently on, what are your thoughts about using options like -f wrap v in GCC instead, which forces wrapping behavior for signed integers? Let's say from your source code, you will not know if that flag is set or not. So depending on the environment, your code will have undefined behavior or not. And in a safety critical environment, that's really, it's possible to do if it's well documented and well understood and enforced and checked throughout your build that it never compiled differently. And I would say that's possible, but I would not recommend it. So one of the reasons I played around with concepts and my idea to provide this safer integer arithmetic is also limiting the possible arithmetic. And I'm not sure what wrap v is actually doing with division by 0. And shifting, it might actually do something same, but I haven't checked that. So I don't have much experience with the wrap v flag to actually make sure it's if it's really enforcing wrapping for signed integers. And I'm not even sure if it's considered by standard numeric traits of int to actually mark is modulo correspondingly. I would need to check that, and I cannot answer that right now. And there were also some comments on the chat. Okay. And Robert actually answered for me the question that specialization is good for non-arithmetic types. And I'm sure I stole the idea of specializing numeric limits from his safe int library. So I think we have answered all questions. There's nothing more in the chat I see the ability to comment on. Just to remind you that if you're writing safety critical code, I'm available for giving feedback and reviews and other consulting and training around that. So let me advertise that a little bit. Try out the library, give me feedback, either file issues or reach out to me by email or Twitter. And if you liked it, tell others. If you didn't like it, tell me. And the best to give suggestions for improvement in the end. Otherwise, I wish you a good rest of CppNow, and hopefully see you again in person next year in Aspen or whenever we have the ability to meet again. Goodbye.